Hey, how's it going? I'm giving this a shot for the first time ever, so hopefully this works out all right. But since we missed lecture on Thursday, let's do a recording and talk about carboxylic acids and esters. So right after this, I will make it to where your homework is available for chapter 16. But before you start working on that, I want to let you know of a few hints. There's going to be a couple questions where it says please include charges, so don't forget that. In order to do that, you must click on the atom that has the charge, and then click the plus minus button that's in sapling, and then you use your keyboard keys to either put in a negative sign for if it's a negative and a positive sign if it's positive. So that's on that specific atom that has the charge. Also, I typically say water can be represented as HOH, which is true. However, sapling does not recognize it, so please make sure that you write water as H2O and not as HOH. Alright, carboxylic acids. So a carboxylic acid combines both the carbonyl group, which is a carbon double bond oxygen, with a hydroxyl group, which is what we see in alcohols. Now when these two are attached to the same carbon, this is when we get a carboxyl group. So here, carbon double bond oxygen, also to an OH. This is not a ketone, not an aldehyde, and not an alcohol. When you see both of these attached to the same carbon, this is a carboxylic acid. Okay. You can also see this written as RCOOH or COO, which is the carbon double bond oxygen, oxygen H, or if you're feeling particularly lazy, you can always write RCO2H. So let's do some naming, nomenclature of these guys. So the root name is based on the longest chain containing that carbon atom, so containing this carbon atom that's in the carboxyl group, this guy being the carboxyl group. You drop the E and it's replaced with oic acid. Now the carboxyl carbon, that's this guy, is assigned number 1, but you don't need to include it in the name because this guy has to be at the end of your carbon chain. There's only one direction, and this will be carbon 1, then 2, so on and so forth. So let's do one together. We have 1, 2, 3, 4, 5, 6, 7. So that's heptane. Heptane is the longest carbon chain that goes through the functional group. Then you're going to drop the E and add oic acid, so heptanoic acid. Again, you do not need the number 1 because carboxylic acid has to be on carbon number 1, meaning that if we start here, this has to be carbon number 1. We have no other direction to go except for identifying the longest chain. Alright, so let's do a few more. We got one carbon here, methanoic acid. This is found in bee stings and ant bites. 2 carbons, ethane, drop the E, add oic acid. Ethanoic acid, this is the same thing that is found in vinegar. 1, 2, 3, propane, drop the E, add oic acid, propanoic acid. This is found in Swiss cheese. And then butane, this is butanoic acid. Could do a few more examples. 2 carbons with the carboxyl group. This is ethanoic acid with the bromine coming off of carbon number 2. So 2-bromoethanoic acid. Benzene ring with a carbon here. This is going to be benzoic acid. Once you have a benzene ring that only has 2 functional groups on it, this is when you can use meta, ortho, and para. So we've got the benzene group with the carboxyl group. This is named as benzoic acid. And then bromines off of 1, 2, 3, 4. So 4-bromobenzoic acid or p-bromobenzoic acid. Alright, so I'm going to have to do that every time 5 minutes comes about just because it seems to shut off on me every 5 minutes. So let's do another example. So with this guy, don't forget to find the longest carbon chain that goes through your highest priority. So we have a carboxyl group and a hydroxyl group. The highest priority is this guy, your carboxylic acid. So this is going to be carbon number 1. Now find the longest chain that goes through there. Whoa, my pointer, there it is. 1, 2, 3, 4, 5, 6. Yes, we can go down so then we can find the longest carbon chain. So we have heptane, drop the E, add oic acid, so heptanoic acid. To say that we have this OH group coming off of carbon number 2, we say 2-hydroxy. And then 1, 2, 3, 4. There's 4-methyl. Now don't forget to put that in alphabetical order. So 2-hydroxy, 4-methyl hexanoic acid. Here's another example. 1, 2, 3, 4, 5. So 5 is pentane. Drop the E, add oic acid, pentanoic acid. This guy has to be carbon number 1. So 1, 2, 3, 4. So we have 3,4-dichloropentanoic acid. 3,4-dichloropentanoic acid. I don't know why I said that twice. Alright, so some additional tips for nomenclature with carboxylic acids. So as we discussed in the previous slide, when a carboxyl group is found with a hydroxyl group, the carboxyl group gets the highest priority, or your carboxylic acid gets the highest priority. So in order to name your hydroxyl group, you say it's a hydroxy, and then say what carbon number it is coming off of. Now, common names will incorporate Greek letters instead of using numbers. So far what we've been using is we've been saying 2-hydroxy or 3-hydroxy. Common names use alpha and beta, where alpha is going to be the carbon right next to your carboxylic acid. So this is carbon number 1 always. So then the one next to it is alpha. And then keep going down your alphabetical letters for Greek letters. The next one would then be beta. So lactic acid, which is the acid buildup after exercising, that's what gives us that soreness. The common name for that is 2, so 2-hydroxypropanoic acid, but you can also call it alpha-hydroxypropanoic acid. You will need to know both of these because you will see both of these. Alright, so melting points and boiling points of carboxylic acids. If you take a look, there's a lot of polarity going on here. We've got carbon with a partial positive, this oxygen with a partial negative. This oxygen also has a partial negative, which then causes this hydrogen to be partially positive. So lots of polarity going on here. And then on top of that, when you have one carboxylic acid interacting with another carboxylic acid, you can actually form 2 hydrogen bonds. See that? 2 hydrogen bonds. So because of that, these guys are going to have particularly high melting points and boiling points. So let's take a look of a few. Alkane, pentane has a boiling point of 35. Ether, diethyl ether, for an example, my favorite, got the spider, boiling point of 37. Aldehydes and ketones are often very similar. 76 and 80, that's because we have a dipole moment going on. This carbon's partially positive, this oxygen's partially negative. Same thing here, this carbon's partially positive, this oxygen's partially negative. So we have some dipole moments going on. Alcohols, then there's a pretty big jump between your aldehydes and ketones to your alcohol. And that's because we can do hydrogen bonding. So if I had another one above, this oxygen could be interacting with the hydrogen from the other alcohol. And then carboxylic acids. This one can hydrogen bond in 2 locations as shown on the previous slide. So that's why there's another jump here. So solubility usually goes hand in hand with melting points and boiling points. I'm going to give this a pause just so I don't lose out again. All right, and we're back. So solubility tends to go hand in hand with melting points and boiling points. Carboxylic acids have the highest melting point and boiling points, and the reason being is because they love to hydrogen bond. Another molecule that loves hydrogen bonding is water, so which is why carboxylic acids dissolve so easily with water. So again, lots of locations for water to interact with that carboxylic acid, which really means that they like to dissolve in each other. So acids up to 4 carbons are very soluble, 5 and 6 are slightly, and 7 and up are insoluble. So the general rule of thumb, as 5 or more carbons, it decreases solubility. So again, increasing and boiling point and solubility order are about the same, which is hydrocarbons, then ethers, aldehydes and ketones, alcohols, and then carboxylic acids. All right, so let's do a few examples, or let's do a few practice problems. So let's order the following from lowest to highest boiling point. So we have hexanol, hexane, hexanal, and hexanoic acid. So all of them have the same number of carbons, so we can ignore that. So biggest factor that's changing, OL is an alcohol, ANE is just a carbon-hydrogen chain or alkane, AL means you're dealing with an aldehyde, and then oic acid are those carboxylic acids. So alkanes have the lowest, as we have been learning. Hexanoic or oic acids have the highest. So we have our lowest is hexane, our highest is hexanoic acid. So then let's look at the two that's in between, alcohols and aldehydes. So between those two, alcohols can hydrogen bond, aldehydes cannot. So because of that, alcohols will have the second highest, hexanal will have the second lowest. So here we go. Hexane, hexanal, hexanol, and then hexanoic acid. So boiling points in order are listed there just for your information if you'd like. So let's then talk about solubility. Which of these would be the most soluble in water? Butane, butanoic acid, butanal, and 1-butanol. So it's asking for the most soluble in water. So as we've been learning, carboxylic acids have 2 places to hydrogen bond. Water loves to hydrogen bond. Like dissolves like. Therefore, butanoic acid would be the most soluble in water. Another question I could ask on the exam is which one would be the most soluble in oil? Now, have you guys ever tried to mix water and oil? Doesn't work out very well. So things that are very soluble in water are not soluble in oil. Think of it the other way around. Things that are not soluble in water are soluble in oil. So butane, which is not very soluble in water, could be or is soluble in oil. That's another question I could possibly ask on the exam. All right. Whoops, didn't mean to do that. Which of these would be the most soluble in water? So again, I'm asking about the most soluble in water. So we have ethanoic acid, decanoic acid, hexanoic acid. Oh my goodness, they're all oic acids. So what do I do? So if you recall, if it has less than 5 carbons, the more soluble it is. Or the smaller the number of carbons, the more soluble it is. So ethanoic acid has the least number of carbons, so therefore it's going to be the most soluble. Alright, which of the following would be more soluble in water? So again, all of these are within the same molecular weights. We have butane, propanol, and ethanoic acid. Since we're dealing with water again here, we want the one that can do hydrogen bonding. Ethanoic acid is the best. If I asked which of the following would be more soluble in oil, that would be the one that's least soluble in water. So that would be butane. Alright, so do you guys recall acids and bases from Chem 101? I think you guys also had a little refresher on this in this week's lab. So acids are compounds that can either donate or give up a proton. A proton is the same thing as a H+. Bases are compounds that can accept protons, again where protons are H+. Another way to look at it are acids are givers and bases are takers. So rude, so rude. So let's do some practice. Label each compound as an acid, base, salt, or neither. So let's look at A here. Is that an acid, base, salt, or neither? It's an acid. The reason being is because HCl donates H+, or it donates protons. You'll probably hear me say donates protons more often than anything else. So HCl will give up a proton and a chloride. Let's take a look at sodium hydroxide. What does that guy do? We'll split that guy up. What ions does it make? Sodium hydroxide makes sodium and hydroxide. This is going to be a base because it accepts protons. This hydroxide here is going to be attracted to the H+, and when these two come together, what does it form? Forms HOH, or water. Again, sapling only accepts H2O, so don't forget that. Okay, CH4, methane. We know what that guy is. Acid, base, salt, or neither. Is there any place for it to accept protons? Again, protons being H+. Any place for it to donate a proton? Carbons like their hydrogens, they're not going to give them up. So this is an example of neither. It doesn't accept nor donate protons and doesn't form charges. The reason why that is important is for salts. Salts will form charges. Kind of like this next guy here. So if we look at sodium chloride, this is table salt. This is the salt we eat. That white stuff that we put everywhere and we probably shouldn't have too much of. Yeah, that guy. So NaCl, table salt, is a salt because it forms charges, but it does not accept or donate hydrogens or protons. So sodium chloride will dissociate into Na plus and Cl minus, but neither one of those guys are going to accept a hydrogen or donate a hydrogen. So this one's tricky. This one's tricky. So you see this OH right here? This is not a hydroxide. This is not the same as this guy. Okay. This guy's a hydroxide because it is bound to a metal, where sodium is a metal. This OH here is attached to a carbon. Carbon is a nonmetal. Therefore, you do not want to think of this OH the same as this OH here. Instead, it's going to actually act different. This is a weak acid. And that's because the hydroxyl group, this OH here, donates a proton. So this CH3OH actually dissociates very, very slightly, which is why it's a weak acid, into CH3O minus and H plus. But this is a very weak acid. All right, so let's talk about the acidity of carboxylic acids. So what do you guys think this is? It's an acid because acid's in the name, right? Okay, so we have this guy right here. Where is the hydrogen that's going to be given away? There's only one hydrogen to choose from. Yeah, this guy right here. So this is going to be the acid part and give away its hydrogen. Water here is going to be what acts as the base, so it's going to accept the hydrogen. And that's how we form what's called a carboxylate ion. So it kind of sounds like carboxylic acid, right? But it's carboxylate ion and then hydronium ion. That is when you have an H plus with water that forms a hydronium ion. So hydrogens that are attached to a carbon, so if there was any hydrogens attached to this carbon, those are not acidic. Do not ever remove those hydrogens, okay? All right, so I'm going to give you some practice. Draw the conjugate base of this following acid. All right, so did you guys give that a shot? Did you try to draw out the conjugate base of this guy? If not, I can give you a hint. So when you take a look at your two reactants, you need to identify which one's your acid and which one is your base. If you think about the name, this is called a carboxylic acid. So this guy's going to be your acid. What do acids do? They donate their protons. Acids are givers, which means this guy is your baser, and bases are takers. So your acid will donate your proton. Again, proton is the same thing as your H plus here, whereas bases, they will accept the protons. So redraw these, except that with your acid, it's going to lose its proton, so redraw it with that one. Your water is going to accept it, so add the proton. Okay, so I redrew this guy, but without the proton or without that hydrogen, and then my water here gained that hydrogen. All right, also notice that we form charges. Again, this is when in sapling you want to make sure you include your charges. So we have a negative charge on this oxygen. The reason being is because it lost a proton, which is positive. So you become more negative once you lose that positively charged proton there. Water accepted that proton, so it became positive. Alright, so neutralization reactions. This is what happens when you mix an acid and a base together, and it forms water and salt. So we have an acid reacting with a base. It's going to form salt and water. Always, at least in this class. So with carboxylic acids, if you react that with a base, you're going to form carboxylic acid salts. So here we have two carbons, ethanoic acid, this potassium hydroxide. So we have an acid, we have a base. That means we're going to form salt and water. Here we go, salt and water. So again, your acid's going to give up this proton. This proton is going to be attracted to your OH, because your OH, or your hydroxide here, has a negative charge. So we have HOH. Again, sapling does not accept HOH as water. You will have to write it as H2O. And then that means this potassium here is going to be attracted to the rest of this molecule because it now has a negative charge after it losing a proton. So your potassium will be attracted to this guy. They'll balance each other out, and then you have your water. Now when it comes to naming salts, so to name a carboxylic acid salt, you have to drop the ic, or the ic acid. So ethanoic acid, drop the ic acid, and you're going to add 8. So ethanoate. So ethanoic now becomes ethanoate. So to name this, don't forget you have potassium, so we have potassium ethanoate. All right, esters. So esters are the ones that create good smelling compounds. These are great. I love these. So flowers. So when you go over and you smell flowers, that's usually because of the esters that are present in them. Fruits can smell good because of the esters that they have. So this is very opposite from thiols. If you remember thiols, thiols are the ones that have an SH. That's what we found in skunks. That's what we find in farts. That's what we find in rotten eggs. Those are the bad smelling stuff. Esters, they're good. I like those. They're flowers. I like flowers. So esters are formed when you have a hydroxyl group of a carboxylic acid is replaced by an OR group from an alcohol. So the generic form is written right here. And I'm hitting my 5 minutes, so I'm going to take a pause, come back in just a second. Alright, and we're back. So esters are formed when you have a hydroxyl group of a carboxylic acid is replaced by an OR group from an alcohol. So what does that look like when you combine the two? That means you're going to have a carbonyl, so carbon double bond oxygen, attached to a COR group. Okay, so this is not a ketone. This is not an aldehyde. This is not a carboxylic acid because this is not a hydrogen right here. This together is what we call an ester. So the way that I remember the difference between ethers and esters, right, they sound very, very similar, is that ethers only have the one oxygen, whereas esters have this S. When you write S's backwards, they look like twos. So those are the ones that have two oxygens in the middle. That's how I remember it. See if it helps. All right, so esters are formed by reacting a carboxylic acid with an alcohol in the presence of a strong acid and heat. So again, I'm going to put acids and heats either above or below these arrows to show that these are catalysts, which means they help speed up the reaction, but you won't see them in the products. Okay. So we have a carboxylic acid with an alcohol. If you notice, we have an OH group from our carboxylic acid, this hydrogen from the alcohol. What does that form? Yep, that's right. Dehydration reaction. We're losing water in this process, and then that's how this oxygen gets attached to this carbon here, which is how we form our ester. Okay? Oh, yeah. So another way to look at it is you break this double bond, or not this double bond, you break this bond here, and you're going to replace it with the other oxygen. Okay, so dehydration reactions. We have learned a few of these already, so I want to kind of remind you of those. In chapter 13, we talked about the dehydration of alcohols to form alkenes. I'll show you that on the next slide. Chapter 14, we lost water during the formation of acetals. In chapter 15, we also lost water during the formation of the glycosidic bonds. So I'm going to show you these really quick, so then just to kind of refresh your memory and to show you that this is going to be very similar to what we see with esters. All right. So chapter 13, reaction of alcohols. This is when we have an intramolecular dehydration. Intra is within, which means we're going to lose water within that same molecule. So alcohols, you're going to lose the OH, which is the alcohol portion, and look off of a neighboring carbon, and then we'll lose a hydrogen from over there. Once it loses this water, which is HOH, again, sapling does not recognize this as water, so make sure in sapling you write it as H2O. Once this guy loses its water, these carbons then only have 3 bonds. 1, 2, 3. 1, 2, 3. So to make them happy, we put a double bond between the two. So now they all have 4 bonds. Again, this is in the presence of an acid, which can be represented as H+, and heat. 180 degrees Celsius is quite a bit hotter than room temperature, which is 25 degrees Celsius. All right. Don't forget Zaitsev's rule, which is the dominant product is the one with the most alkyl groups attached to the carbons of the double bond. If that doesn't make sense, remember the poor get poor, which means the hydrogen is removed from the carbon that starts with the fewest hydrogen atoms, the opposite of Markovnikov's. So if you take a look here, this is the carbon that the OH is attached to. Look at your neighboring carbons. Which one has the least? The CH2 group does. So because of that, this is where your double bond is going to form, which is shown here. And you lose water in the process because it took that hydrogen off. All right, so in acetals, acetals are formed when a hemiacetal, so So we got our OR group, carbon, and an OH, hemiacetal, reacts with another alcohol. Now this is an example of an intermolecular dehydration, where inter means between two people, between two molecules. It means between two or more things. So this is different than the one that we just saw on the previous slide, which was an intra, which means within the molecule. This means we're losing water between two molecules. So you can look at it as this OH combines with this hydrogen. When these two come together, you lose water. That made it to where this carbon here lost a bond, right? It lost this OH bond. So it needs another bond to be happy. This oxygen also lost a bond because it lost this hydrogen. And so it also wants to form another bond. Well, let's make it to where they make each other happy. So they come together, everybody's happy, we form an acetal and release water. So again, this is a dehydration, but it's an intermolecular dehydration because it was between two molecules. This is also usually done in the presence of acid. There we go, H+, acid. All right, and then chapter 15, when we just went over not too long ago, we lose water whenever we form disaccharides. So again, this is another example of an intermolecular dehydration. We have two monosaccharides here. They're going to lose water in the process. Doesn't really matter which way you look at it. OH, OH, you're going to lose water during that process. Leaves one oxygen left over. This oxygen is then going to bond to this carbon. And that's how we form our glycosidic bonds. So again, lose water in the process. This is a dehydration reaction. So, bringing it back to esters, let's take a look. We have a carboxylic acid. We have an alcohol. We're going to lose water in the process. Where does that bond break? It breaks right here. So we have our OH. Going to react with this hydrogen here. There's our water. Now this carbon only has 3 bonds. 1, 2, 3, because it lost this one. This oxygen lost this bond, so it only has 1 bond. So they're going to come together, make each other happy. Now we have it to where this carbon has 4 bonds. This oxygen has 2. Yay! So everybody's happy. This bond right here, this is what we call the ester linkage, because we need the carbon double bond oxygen, carbon single bond. We need all of this and then that to make an ester. And this part right here is how we formed that ester. So this is called a dehydration or an intermolecular dehydration. But to be more specific, the better way of naming this is an esterification reaction, because you formed an ester. You will do this in lab. In fact, you will do this in your aspirin lab, where you're going to remove water, or maybe even completely remove water. I can't remember. It's going to be showing up here in the next couple slides. But you're going to do this in your aspirin lab, where you're going to have very little water, which means your reaction here is going to shift towards your products. This is Le Chatelier's principle. Hopefully you looked over that video. So if we take away products, that's going to shift the reaction to go towards the products to balance it out again. Alright, let's do some practice. We've got a carboxylic acid here. We have an alcohol. This is done in the presence of heat and acid. What do you think you're going to lose? Okay, I'm going to pause here. You practice this. Alright, so hopefully you gave this a shot and you tried to draw the products. I tried to give you a little hint there. Acid, heat, we'll be talking about dehydration reactions. So yes, so this is going to be another dehydration reaction. So take a look, color coded it for you. We have our carboxylic acid, we have our alcohol. We're going to break it right here next to that carbon double bond oxygen. That gives us our OH, which means it needs another hydrogen to form its water. That's how we have formed the water over here. Again, this carbon's no longer happy, it only has 3 bonds. This oxygen's no longer happy, it only has 1. So they're going to come together and form an ester. Alright, so esters do have their own nomenclatures. If you've noticed, we have been talking about how esters are formed from carboxylic acids and from alcohols reacting together. So when it comes to naming these things, we're going to name it based off of the carboxylic acid and the alcohol that was used to make it. So if you take a look here, here's our carboxylic acid, got 2 ethanoic acid. Here we have our alcohol, we got 2 carbons, ethanol. So when we take a look at this guy, we have the carboxylic acid came together with the alcohol portion, formed water. Now between these two, between ethanoic acid and ethanol, do you remember which one has the highest priority? Look at the carbon that has the most oxygens. This guy has the highest priority. That being said, when we name our esters, we're going to have it to where our base is going to be based off of our carboxylic acid. Okay, so what do I mean by that? So look here. So red, that's this ethanoic acid, ethanoate. It now became ethanoate, just like how we named carboxylic acid salts. Drop the ic acid, add ate, ethanoate. That covers this portion right here. Then this part that comes first, this is going to be your branch, just like an alcohol would be considered a branch on a carboxylic acid. This is the portion that names the alcohol. So ethanol was the alcohol that was used to form this ester, so that's the ethyl. So here's the ethyl portion. I should actually include this oxygen. That's the ethyl portion. Okay, so ethyl ethanoate is used in non-acetone nail polish removers. That's propanone. Acetone is propanone. So remember, acids have priority. Sorry, that took me a second. Remember that acids have the priority. Ethanoic acid has the priority. So that part of the acid is named last. The alcohol is the substituent or the branch. That's the case even if the alcohol has more carbon atoms than the acid. Okay? I will definitely test you on that. Absolutely. Okay? So let's do another example. So we're going to name this ester that is synthesized by the following reactants. So we have an alcohol. We have the carboxylic acid. So let's do that. Our alcohol is methanol. Our carboxylic acid, 1, 2, 3, propanoic acid. Now between these two, which one has the highest priority? It's the acid. And so when we come and name our ester, we're always going to look at the carbon that's attached to the carbonyl. And that is the base name. So that's our propanoate. Again, we're going to drop the ic acid and add O8. Then, after naming your highest priority part, you're going to add in your branches. And the way that we named the branch on this is a methyl group. So, because it came from methanol. And then we lose water in the process. Again, heat and acid is a catalyst, but you don't see an extra hydrogen here, and you don't see heat over here. So if you're given the name of the ester, you should be able to draw its structure, where the substituents can be attached to either the alcohol or the acid end. So let me bump this up a bit. 2-methyl-pentyl, 3-methyl-butanoate. What is that, right? So the first thing you want to notice is you have the alcohol portion and you have your carboxylic acid portion. All right, so again, you want to take a look. Notice that you have the alcohol portion of it listed first, followed by the carboxylic acid portion listed last. So, working backwards, let's look at the carboxylic acid portion. It's a butanoate. So we've got 4 carbons in there that's attached to the carbonyl. Right? This carbonyl is what comes from your carboxylic acid. So butanoate is, there's 4 carbons attached to the carbonyl portion. And then if this is carbon number 1, count over 3, and there's a methyl portion coming off of that. Okay, I'll show you what it looks like here in just a second. So let's talk about the alcohol portion. The longest part in the alcohol is your pentyl. So we have 5 carbons. So on the alcohol portion, there's going to be 5 carbons here. And then this is going to, the carbon that's attached to your oxygen is going to be carbon number 1. So this next carbon over from that is where you're going to have a methyl. So let's take a look. We have butanoate. So this is the one from the carboxylic acid. That's the one that's attached to the carbonyl, right? The carbonyls from your carboxylic acid. So right here, we have our carbonyl. We have 1, 2, 3, 4 carbons. If you don't like the line structure, here's this one. We have the carbon attached to the double bond oxygen. This is our carbonyl. This is our carboxylic acid portion. Carbon number 1, 2, 3, 4. So there's our butanoate part. Then we have the 3-methyl. So 1, 2, 3, 3-methyl, or 1, 2, 3, 3-methyl. All right, so that takes care of the carboxylic acid side of our ester. Now we have to look at our alcohol side. So attached to the oxygen, there's going to be a 5-carbon chain. So take a look here. 1, 2, 3, 4, 5. So there's our pentyl. And then the carbon coming off of the oxygen is always going to be carbon number 1 in our esters. So that means 2-methyl is coming off of carbon number 2. Here's carbon number 2. There's our methyl. Okay. I'm going to go back to looking at this side. This is our alcohol side. So that's dealing with the 2-methyl pentyl. The pentyl means there's 5 carbons coming off of the alcohol side. So 1, 2, 3, 4, 5. And then again, the carbon attached to the oxygen is going to be carbon number 1 when it comes to esters. And then 2-methyl means off of carbon number 2, we have a methyl group. So again, you really have to look at esters as where did it come from? They come from a carboxylic acid. They come from an alcohol. That's how we name it, is based off of the carboxylic acid and the alcohol that was used to make the ester. The second half will always tell you the carboxylic acid portion, which is going to be the side that has the carbon double bond oxygen. Because again, the carbon double bond oxygen came from your carboxylic acid. When it comes to the first part of our ester, that is looking at the alcohol portion of our ester. So, take a look here, the alcohol portion. Okay. So even if this one has more carbons, which this one does, 1, 2, 3, 4, 5, 1, 2, 3, 4, you're still going to name it based off of your carboxylic acid, where it starts. So right here, this gets highest priority, even if this one has the longer chain. Okay? All right, I'm going to pause this before moving to the next one. All right, so aspirin is an ester where it's made from salicylic acid. This is your carboxylic, nope. This is your alcohol, sorry. Salicylic acid does also have a carboxylic acid in there. And this is also the common name for this, not the IUPAC. But in the salicylic acid, this is the alcohol where we react it with acetic acid, or the way that IUPAC would name it is 2 carbons, ethanoic acid. So we have our carboxylic acid reacts with the alcohol portion on salicylic acid to form aspirin, where aspirin, the compound name is acetyl salicylic acid. Again, this is the common name, not the IUPAC name, so I'm not going to test you on this. But again, these things can look complicated, but it's the same thing. We have our alcohol reacting with our carboxylic acid. They're going to come together to form our ester, so carbon, double bond oxygen to another oxygen here. So here's our ester, and it releases water in the process. If you open an old bottle of aspirin, so a few years ago, you find you bought some aspirin, it's still sitting in there. If you smell vinegar, so vinegar, if you remember from, I don't know, slide 3, it was a long time ago, right? Vinegar is ethanoic acid. So if you open that bottle and you smell that vinegar, you're smelling the ethanoic acid, which means this guy has degraded. See the double arrow goes back and forth. This guy has reversed back into ethanoic acid and salicylic acid, which means it's no longer going to be very effective, so not a good idea to use it. When it comes to your aspirin lab, you're not going to use acetic acid. Instead, you're going to use something that's called acetic anhydride. I don't think we talk about anhydrides in this class really. So you don't have to really worry about naming this. But here is acetic anhydride. Here is salicylic acid. The key thing that I want you to see from this slide is, do you produce water? Do you see water? No water? Nope. I don't see no water. The reason is because we used acetic anhydride instead of acetic acid. What that does is it gets rid of this equilibrium. On the previous slide, I'm actually going to go back. There was this equilibrium arrow right here, right? It goes back and forth. That's because water will hydrolyze this guy and make it go back in the reverse direction. So this can go in the forward direction. This can go in the reverse direction. The water's kind of the key thing for that. If you notice, no water. So because of that, this goes very favorably only in the forward direction, which is why there's only a single arrow here. Still have acid, still have heat to help make this guy proceed in the forward direction. But what that means is in lab, you should make a lot of this guy. Yep. So again, notice that I changed the arrow only to the forward direction instead of equilibrium. Equilibrium, forward direction. Okay? So in your lab, you're going to be making aspirin with these two compounds. It's going to be very favorable. You're going to make a lot of it. In fact, if I remember correctly, your whole solution will practically turn into a solid when you start to recrystallize it. And that's because this is so favored. Okay. Besides that, that slide was just to kind of give you a heads up about lab. All right, so solubility of esters. They are going to be slightly more soluble than ethers. So hydrocarbons, ethers, then esters, then esters. Again, the way that I remember it is esters. S, if you do it in the reverse direction, kind of looks like a 2. So esters are the ones with 2 oxygens, aldehydes, ketones, alcohols, and carboxylic acids. So I gave you a list here just to kind of show you what that looks like. Here's our ester versus our ether. Okay. All right. Can't get away from those reactions. I'm going to actually pause here. We'll start here in just a second. All right, so reactions, hydrolysis reactions of esters. There are 2 different kinds. So 2 different ways where we can split up that molecule. We've got acid hydrolysis and base hydrolysis. Okay, number 1, acid hydrolysis. So hydrolysis is hydro lysis. So we have lysozymes in our body. They break up molecules. Lysis means breaking stuff up as well. Hydro means water. So this is saying that you use water in the presence of an acid to break something up. So that's going in the reverse direction of the formation of an ester. So here, when we formed esters, we used a carboxylic acid, reacted it with an alcohol in the presence of heat and an acid. We then formed this ester and released water. But again, this is an equilibrium, meaning it does not only go in the forward direction, it also goes in the reverse direction. So with acid hydrolysis, we're going to have an ester. We're going to have our water, so our ester, our water. And in the presence of an acid, where acid is acting as our catalyst, it's going to break this guy apart. Okay, so acid hydrolysis. Lysis means break. Hydro means water. We're going to break something with water in the presence of acid. So here's our ester. We have our water. The bond that we're going to break is the same bond that we broke with the carboxylic acid, which is right here. So break that apart. And then, since we're doing this in the presence of an acid, we can reform our carboxylic acid. So here's our carboxylic acid and our alcohol. So again, because this is an equilibrium, this can go in the forward direction and it can go in the reverse direction. This can go in the forward direction. This can go in the reverse direction. All right, so let's do some practice. Why don't you draw the products? All right, so I'm going to assume you gave this a shot. So we have our ester. We have our water. You're going to break it right here, right at that location. And that's how you're going to form your alcohol. See, here's your alcohol half. This is your carboxylic half. Do you remember when we named it? This was the alcohol name. This was the carboxylic acid name. So that's the same thing here. We're going to break this molecule into our alcohol portion and our carboxylic acid portion. Since we're doing this in the presence of acid, we can reform our acid and our alcohol. Okay, trying to emphasize the acid here because this is acid hydrolysis, which is slightly different than the next one we're going to cover, which is base hydrolysis. Okay, so what would cause a reaction to go in the forward direction versus the reverse direction? Did you guys watch that video? The Le Chatelier's principle video that I posted? Yeah? Yeah? Okay. If you have, hopefully that video helped remind you what Le Chatelier's principle means. If you haven't, I would recommend watching it, because all I'm going to say is that Le Chatelier's principle is what causes this to go in either the reverse direction or the forward direction, which states that if I increase something on the product side to balance it, it's going to go shift towards the reactants. If I increase anything on the product side to balance it, it's going to shift it towards the reactants. So Le Chatelier's principle tells us that when you're in equilibrium, it means that these guys are balanced. If you disrupt that balance, it's going to fix it. The video does a much better job of explaining that than I just did. So please watch that if that did not make sense. Okay, so previously I kept saying acid hydrolysis. You can form the acid. This is now base hydrolysis, which means you will not form an acid. Okay? All right, base hydrolysis, which means we're going to use base to break apart a molecule with water. Okay, lysis means break apart, hydro, water, breaking a molecule apart with water in the presence of base. All right, so here's our ester. These again can be split apart. So we have water and our base. Now, because this is under basic conditions, will you produce an acid in the presence of a base? Hopefully you're shaking your head no. No, we cannot. If you recall from previous slides, whenever there's an acid with a base, those two are going to react together to form a salt and water. So it's kind of along the same thought process. If we have a base, you're not going to form that acid, or if you do form that acid, the base and the acid are going to react. All right, so there's kind of two parts to this. At least the way that I'm going to teach it is going to be in two parts. So the first thing again is to break this bond right here. So we're going to break this bond, have it react with the water to form your carboxylic acid and your alcohol. Now, because this is done under basic conditions, we cannot form this carboxylic acid. So this carboxylic acid is going to react with your base, your OH here. This hydrogen here is going to reform your water, which then leaves you with your carboxylate anion. Okay, so base hydrolysis is similar to acid hydrolysis, except for the fact that because you have a base, you will not produce your carboxylic acid. It's going to keep reacting until you form your carboxylate ion. So, give that a shot. What are your products going to be? All right. So if you go through this in steps, kind of like what I showed earlier, you're going to break this bond right here with that water, which means your OH from the water is going to add here, your hydrogen is going to add here. When you do that, that forms your carboxylic acid, right? Your OH is in here now. Your alcohol, there's now a hydrogen attached here, so we have our alcohol and our carboxylic acid. However, since we have this under basic conditions, when we form that carboxylic acid, the acid is going to react with your your base to produce your carboxylate ion and your alcohol. So, under basic conditions, you will not form a carboxylic acid. Hopefully, I've said this enough times. Have you picked up on what I'm trying to say? Okay, I hope you're nodding. If not, come talk to me. All right, let's do a little review. Let's name this following compound. So we need to identify the functional group with the highest precedence, which means highest priority. So we have two functional groups in here. We have an ether, and we have a carboxylic acid. So between these two, which carbon has the most oxygens? That's this guy. So this is going to have your highest priority. So you need to identify the functional group with the highest precedence. That's your carboxylic acid. This will be given to you on the exam via the table, which is at the end of this PowerPoint. Then you're going to name the compound based on the longest chain that goes through that functional group. So identify your highest precedence functional group. You must go through that functional group. So this right here is carbon number 1, 2, 3, 4, 5, 6. So hexane, drop the E at oic acid, hexanoic acid. Now we need to determine how to name this branch. When it comes to ethers, we have to use the IUPAC way of naming it as a branch. This carbon is included in our longest chain, so we do not need to include this when we name it as a branch. So instead, look on the other side, only one carbon. So this is a meth. To include this oxygen is called methoxy. So 1, 2, 3, 4, 5. This is 5-methoxy. So 5-methoxy. Put this together, and if multiple branches, make sure it's in alphabetical order. We only have the one branch, so now we have 5-methoxyhexanoic acid. 5-methoxyhexanoic acid. Yay! I believe this is it. Thank you. If you did actually listen to this, I really, really appreciate it.